The 196,000 gallons of liquid oxygen and the 537,000 gallons of liquid hydrogen will combine to provide 8.5 minutes of propellant to the 4 massive RS-25 engines mounted below. As proven workhorses of the shuttle fleet, each RS-25 engine has a legacy all its own. Together, these 4 engines provide 2 million pounds of thrust, and with the SRB, are capable of pushing Orion peacefully at 17,000 miles per hour. The Aram cryogenic propulsion stage is a 45-foot-tall upper stage that offers Orion nearly 25,000 pounds of thrust. Performing 2 separate burns, the ICPS will first raise Orion's orbit, and then, later, propel it out on a trajectory to the moon. The ICPS is powered by a single RL-10 engine that will perform these 2 burns. This storied engine has propelled robotic missions to every planet in the solar system, including Voyager 1 and Voyager 2, the first space probes to reach interstellar space. Orion's service module, provided by the European Space Agency, is the powerhouse that fuels and propels Orion in space. It stores the spacecraft's propulsion, thermal control, electrical power, and critical life support systems, such as water, oxygen, and nitrogen. Orion's crew module is the pressurized segment of the spacecraft, where future crews will live and work on journeys to the moon. Capable of accommodating 4 crew members for up to 21 days, this capsule includes state-of-the-art avionics, innovative crew systems, and the largest heat shield of its kind for entry back into the Earth's atmosphere. Positioned at the top of Orion is the Launch Abort System, designed to pull the crew to safety in the event of an emergency, on the pad or during launch. 3 solid rocket motors can activate in milliseconds. Now fully assembled, Artemis 1 stands at 322 feet. Artemis is no longer a series of separate parts and programs. United together, this is the first of Artemis's arrows, capable of ushering in the next chapter of human lunar exploration. Only together, this mighty system represents all that is possible, all that we are capable of when united around a stunning vision, with each component playing its part in a grander effort. We, the people of NASA and our partners, we, the people of the Artemis generation, all around this beautiful world, will bear witness to what we are capable of. Together, we are going back to the moon.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times.
Wheels off the ground air.
You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
NASA celebrates Asian American and Native Hawaiian Pacific Islander Heritage Month.
3, 2, 1, 0.
When you think of NASA, you probably think of this. But as soon as we made it beyond the limits of our atmosphere, one of the first things we did was turn our cameras around and look at this. The first U.S. satellite was launched in 1958. That's 11 years before Neil Armstrong became the first person to walk on the moon. Explorer 1, built at the Jet Propulsion Laboratory, initiated a long legacy of satellites meant to take our understanding of Earth to new heights. In 1997, NASA launched a satellite that began a 20-year continuous global record of the very thing that, as far as we know, makes Earth special: life. While most satellite missions capture data on the physical characteristics of our planet's climate and weather, others allow us to measure life itself. The result? The most complete view of global biology to date.
The greatness of this data set is kind of hard to explain. It allowed me to understand ocean in such an organic way.
That's the voice of oceanographer Dr. Ivona Setenik. Ivona and the rest of the NASA Goddard Ocean Ecology Lab help oversee the 20-year dataset. If you take a closer look at this animation, you'll see what looks like a repetitious ebb and flow on the land and surface of the ocean. We're actually watching the planet breathe.
About half of the total photosynthesis on the planet occurs on land and half in the oceans.
That's Dr. Compton Tucker, who pioneered satellite monitoring of vegetation on land. The spring and summer months kick off the growing season for plants on land, illustrated in dark green, and tiny microscopic plant-like organisms in the ocean called phytoplankton, seen in the light blue. They take carbon dioxide out of the atmosphere and use it for energy, causing the total amount of carbon in the air to drastically drop. The opposite is true during colder months. During winter in the northern hemisphere, which is home to most of Earth's land plants, carbon in the atmosphere increases as plants go dormant. And then there are extreme zones in the ocean. Purple patches are nearly devoid of any phytoplankton. They're basically deserts at sea, while the red zones tell us that there's either a high concentration of phytoplankton hugging the coastline, or our satellite sensors are picking up on another input changing the color of the water.
We have a marvelous biological diversity of plants and animals, both on the land and also in the oceans.
But hold on. If we have an amazing biological diversity of plants and animals, why do scientists spend all of their time observing plants?
You know how they say you are what you eat? In the same way, if we want to understand the ocean and life in the ocean, we have to start from the base. If phytoplankton is changing, the whole ecosystem will change.
The changes that Ivona is talking about are much easier to see when we can study a continuous global record. And that means not only being able to look into the past, but also into the future.
It's this long-term data set that allows us not only to see exactly what's happening, but to be able, so much better way, to predict what's going to happen.
A global perspective gives scientists the power to forecast events like harmful algal blooms, disease